Turns out, if you have a 1,3-dicarbonyl compound in which you have two esters on either side of the central carbon, the exact same process can occur, only now we're going to end up with acetic acid derivatives. So we can see that we still retain the acetic acid component, and we have the decarboxylation on the other side. So this is mechanistically identical to what we saw before. We just end up making different sorts of alkylated acids. So I'll go through this a little bit more quickly. The arrows don't change. We're going to have sodium methoxide, let's say methyl iodide this time. This will let us do a single alkylation. If you wanted to add 2 equivalents of methyl iodide, you could do that as well. In fact, let's do this. Let's say 2 equivalents just for fun. This would be able to react twice in a row. We're going to have the sodium hydroxide followed by an acidic workup. Now we end up making 2 different carboxylic acids. Both of them get hydrolyzed. Which upon heating still lets us do the same sort of intramolecular loss of carbon dioxide to give us this unusual enol of a carboxylic acid, something that definitely does not have a favorable equilibrium, that'll quickly tautomerize back to the original carboxylic acid. So when doing retrosynthesis, this actually becomes a bit tricky to identify because we have to imagine adding on a whole nother ester type group when going backwards. So we'll see a few practice problems to try to map them onto different synthetic targets in the end. But with a little practice, these still become demystified pretty easily. So here's a case where we have also diethyl malonate. We have a 3-carbon chain with 2 bromines on it. So this is a double electrophile. That means that when we add in sodium methoxide and this bis bromide, in the first step, we will do an intermolecular alkylation, where we still have the 3 carbons in the middle. And then this will get further deprotonated to make the enolate again. And now, rather than doing another intermolecular reaction with a different bromide, there's one inside the molecule that it can react with. So this is an exact reaction that I've actually done several times in my life. My PhD was on cyclobutane containing molecules, and I used this exact synthesis up to this point to make both this cyclobutane bis ester, and I also did the decarboxylation that follows as well. So I can verify these reactions actually work. So we're going to do sodium hydroxide followed by an aqueous workup. Woohoo, cyclobutanes. We end up with a carboxylic acid. This once again can have the arrows go in a circle. Now give you a cyclobutane carboxylic acid with just a single carbon. So this is, again, a bit hard to see sometimes, because if you imagine how do you go from here to here, it at first certainly is not very obvious. All right, let's do one more case. Where now we have base, and now we're adding in this CH2CO phenyl. So it might be useful to kind of draw this out first independently, just to make sure we have the right structure we're looking at. So here we have the CH2, the carbonyl, and the phenyl. We're going to deprotonate the malonate, and it can do an SN2 reaction again. So our initial product give a branched ketone here. And then sodium hydroxide and heat, followed by decarboxylation, following the exact same process we've seen a few times already. This allows this to be our major product. So overall, the sort of takeaway image here is for whatever type of Rx you have, we're going to add on essentially acetic acid. So it is kind of like imagining this hypothetical carbanion, which of course can't exist in this form because of pKa's, but it's this general idea that will make these types of acetic acid derivatives. So now let's do some practice with the synthesis. How can we make the starting material to arrive at this final product? So one thing we always want to try to do is map out where does this ethyl acetoacetate fall inside the molecule. So we have these oxygens that can help guide us a little bit. So we have this oxygen that connects all the way through there, and this will represent our main 3 carbons through this system. And we can also see that we have this methyl coming off the side. So really what we need to do is not even a decarboxylation most likely, because we still have this ester intact. We don't completely lose that group. We just have a change in oxidation state afterwards. So from this, we can imagine that this molecule resulted from a full reduction of the corresponding alkylated ethyl acetoacidic derivative. And this could come directly from the starting material by using sodium methoxide and something like ethyl bromide. That would get us there. So you can see that there's a bit more complication once we go to a system that also has the decarboxylation coupled to it. And along with the decarboxylation, it seems we've also had a change in oxidation state. We know that for malonates, these end up being, as I mentioned before, these hypothetical acetic acid enolate equivalents, but we don't have a carboxylic acid in the product. So to make this change, we can imagine retrosynthetically, again using lithium aluminum hydride, to get us back to the carboxylic acid oxidation state that we need. Now we know that we also need to somehow break this bond, because we want to maintain this general framework. And this arose from the hydrolysis and decarboxylation of the resulting malonate. So we'd want to retrosynthetically add on our esters first. And finally, we can go back one last stage. This would be which is going to be our sodium ethoxide and the right electrophile. So in this case, we need to have this 3-carbon electrophile that is branched. So this would be something like this, iodide or halide. We will be able to control the number of alkylations by the number of equivalents that we throw in. And that is how you solve these problems. So there's, I think, a few more examples of these problems in the practice and the recommended problems. And we can always go through a few more of these before the exam so people are comfortable with them.